Let's take a look at how we actually get from the instruction to a particular address. What we're doing is we're mixing in this MC jump lines, MC jump 7, 2, 1, and 0 with 4 bits of the instruction. And when we do that for the load instruction, we get to 88. When we do it for a instruction, this is the load instruction, we get to 88. When we do it for a halt instruction, let's do that one. It's the same bits, but now these values over here have changed. The 0, 1, 1, 1, which is the 7 out of the halt instruction. So we have MC jump 1 on, but now this has changed. We load that in. We end up with this instruction, or this address right here, 1011, which is a B, and 100, which is an 8. So when we load that instruction, we ended up a different place in the microcode, and that's how we implement the load instruction, or get to the not load instruction, excuse me, the halt instruction. So that's what we do, okay, is we're just going to take this, we're going to put it into the decoder, pick those lines, load it into the microcode PC, and we jump to a specific instruction. Now, there are some instructions that have a secondary decode that you have to implement. We'll get to that in a little bit. But if you go back to the code, okay, you'll see that I have put in the addresses for all the different instructions, 80, 96, A, every one of these. They don't have to be in a particular order, just as long as I don't make them overlap. And each one of them is short enough that you should be able to not make them overlap. If your implementation is long enough, you're going to have to do a jump to some other location in the microcode that you haven't used. I didn't have to do that anywhere. So here are the two instructions that I implemented, 88 and 90, which is load and store. Okay, this is part of your homework. You've got those two pieces done. And then here are all the locations for the other instructions. Let's look specifically at the skip instruction, because you have to implement that guy, and that's all the stuff for the skip instruction. The skip instruction has a secondary decode. That means that you end up over here at the beginning of the skip instruction, then you've got to use the mux again to jump to the correct piece, which is the skip less than 0, skip equal to 0, or skip greater than 0. So for the skip instruction, we have a different sets of bits that get loaded from the instruction register. That's bits 11, 10, 9, and 8. And let's say we're doing a skip equals, so that's the values, 0, 1, 0, 0, or hex 4. Okay. We probably want MC jump 7 to be a 0, because we've already used a bunch of locations up there where MC jump is 1. So let's say we set MC jump 6 to be a 1. So we're going to jump to a new location in the microcode memory with those decoded. We could turn these on, but I didn't have to. And when we do that, we end up for that particular one at this location, or a hex 50, 05, or 50 hex in memory for that location. And that's on line 127 of the code up there. Now, you have to do this again, because remember, the compare instructions are looking for some value of is 0. And is 0 is the only thing that's hooked up to the inputs on the mux. So when you get to one of these instructions, you've got to load again to jump, either to have an extra increment on the PC, so you skip an instruction, or to leave off that extra increment. And is 0 is hooked up to mux input 01, okay, as that bit. So we can turn around and we can do another decode to implement the skip instructions. The same sort of thing. We've got to turn on the output. We get that value in there. And if the result register has a 0 in it, then we can input that into the mux. We can load the PC, the microcode PC, and make it skip over an instruction. The last choice on the mux is input 00 on the mux, which I used in the halt instruction. And basically what I did is I made my halt instruction just loop infinitely. But you have all the different lines from the microcode being input into the mux at 0, 0, so you can jump to wherever you want to in your microcode memory with that. So you've got a go-to. Now, some of the instructions require the use of the ALU. There's in the code a comment that has this in it, but I've included it in here as to what the different lines do in the ALU. And if you set the ALU input lines to one of these functions, and you set the other inputs, the A and the B input of the ALU, this is the result you get. And some of these things are like comparison. One, if the AC is less than a 2's complement 0, would be real useful for the less than 0, as in you want to set ALU bit 3, ALU bit 1, you want to take the value in the AC register and output it to the ALU to the A side of the ALU, and then you can get this value put in the result. That value in the result, then you can send to your mux to do a jump or not do a jump based on less than 0. So you do a comparison in the ALU, you get a result, and that's what you use. Let's walk through the add instruction. Not the whole add instruction, but the critical line that controls the ALU. One of these is a add. That's this one right here. A 0, 1, 0, 0, or a 4 hex. Add the result of AC in the bus. That's the A and the B side. So the add instruction. You have to have the ID AC out to ALU turned on. That's the A side of the ALU. You have to have the MDR out. That's the B side. So it's on the bus side of the ALU. And then you have to set the ALU control lines to the correct values to get the result of the add instruction. The other signals will be 0. And turn on the result load line so that it will get data loaded into it. And don't forget that you have to do a microcode PC increment or you're stuck there forever. But that in combination, if you've gotten the right things loaded into the AC and the memory data register, will give you an add in the result register. Then you turn around later in another clock cycle or tick cycle and you transfer the result back to the AC and you've added these things together. At the beginning of each instruction in the fetch, you want to turn on set execute. That turns on the little light, but it also helps with how the machine runs. And at the end of every instruction, you need to turn on ints end to mark the end of an instruction. And you want to turn on ID microcode PC clear to clear the microcode PC so that you jump back to 0 in the microcode to start the next instruction. Probably with the exception of the halt instruction, which you don't want to clear, you want to sit there and halt. So it has a little bit different behavior. Do note that all the instruction lines are case sensitive, so ID AC LD with a capital L is not the same as ID capital AC lowercase ld. And it will not work. Now, I've provided you with both a command line assembler, and you'll notice there's two different assemblers here. There's the microcode assembler, which you can download just like the other things and use it. And there's also an online assembler for the instructions. You have to use both. At the end of each one, when you add this upload flag, it'll give you a big hex number. Let me actually go and run one of these things once, and let's take a look at what that hex number looks like. It did a bunch of things, but at the end, there is this big hex number. I'm going to cut that, and I'm going to take that over to my microcode emulator, and I can say load microcode. And I can put in that big hex number, and I can hit load code, and at this point it will actually load the code that I assembled on my machine into the microcode up here. The same thing happens with the assembler. At the end, if you add that upload flag, it'll give you a big hex code and it'll tell it where to find the file to load that piece of data. So you have the option of using the command line. But in both cases for the assembly, you can also use it directly in the emulator. You can come down here and you can say you want to assemble a particular piece of code. And you click assemble. And it will give you the output from the assembly here. and it will load that immediately into the machine. The same thing works for running with the microcode assembler. Okay, you can put in microcode in here. I think it's a tremendous nuisance to do it this way. I much prefer the command line, but you can put in your microcode in here. Remember, you have to cut and paste this to save it. There's no save button in here, so you want it in a file where you can paste in your microcode. Otherwise, it's easy to lose the microcode that way. And you can assemble it, and it will load the microcode into the microcode memory. So I'm including in this homework final.m2, which was my final version for this homework assignment that includes the stuff that you see. It doesn't have all the instructions. It has 2 sample instructions in there that are part of your homework for this week, or due the 20th, and it's got the addresses figured out. I actually had more trouble testing to get these addresses right than anything else in building the microcode. So I gave you the addresses. You've got to go build some instructions.